Atoms, ions, and molecules rarely exist in isolation, so it's important for us to consider what happens when they meet, and those meetings are described by intermolecular forces. To start, let's just go back to something we already talked about in a previous video. When we're talking about phases, when we're talking about states of matter, one of the things that we can look at is the balance between the kinetic energy, the motion of the particles, and the intermolecular forces, the things that stick those molecules together. So when we're dealing with a solid, the attraction between the particles is usually greater than the kinetic energy, so they stick together. They might vibrate a little bit, but they don't just fly apart. In a liquid, we get to a state where things are just a little bit more balanced. So liquid molecules certainly interact with each other, but they can, slide past. They're not always going to have the same neighbors. They're fluid. When we get to a gas, we get to a situation where, for a couple reasons, the attraction is less than the kinetic energy. So gas particles tend to have so much kinetic energy that it completely overpowers any attraction, any intermolecular forces between them. One thing to remember when we're talking about different phases of molecules, intermolecular forces are kind of determined and defined by the nature of the molecule itself. And depending what the molecule is, those intermolecular forces don't really change. So when we're talking about phase changes, we're not really talking about changing the intermolecular force. What we're talking about is changing the kinetic energy to bounce around between these phases of matter. Let's start with a couple of intermolecular forces that almost aren't intermolecular forces, but they're important when we're thinking about working with matter. Covalent networks are really interesting things because a covalent network solid is really sort of just one molecule. The entire thing is held together with covalent bonds. So in a sense, there are no intermolecular forces. Everything is an intramolecular force. It's a covalent bond. So things like diamond. A perfect diamond is really just one big molecule of carbon atoms covalently bound together to form this three-dimensional covalent network solid. The other one that sort of rides the line a little bit is ionic interactions. So ionic interactions are interactions between oppositely charged particles. They can be very strong depending on the size and the charge of the ions involved. So keep those in mind as we start looking at some of these other interactions and just sort of scaling them to them. So here's a sodium chloride crystal, right? These are all ionic interactions. There's no sharing of electrons going on like over here. Now everything just kind of sits with its own charge. Once we're into the molecular world, one of the most important and one of potentially the strongest intermolecular forces that we work with are dipole-dipole interactions. So a dipole is a molecule that has one end that's a little bit more positive and one end that's a little bit more negative. Now, depending on the nature of the dipole, sometimes it's quite a bit more positive and quite a bit more negative. But the important feature here is because of the molecular structure, this end of the molecule is always positive, this end is always negative, and we end up with something that really looks a little bit like a dipole or like an ionic interaction. But now instead of having complete, full, permanent charges, these are just partial charges. They're not an entire negative charge, it's just a partial negative charge interacting with a partial positive charge. So dipole-dipole interactions are very strong, but they are weaker than a similar ionic interaction. One class of dipole-dipole interactions that's sometimes talked about as a completely different intermolecular force are hydrogen bonds. Hydrogen bonds, really for the most part are just a specific type of dipole-dipole interaction. If you have hydrogen bound to either fluorine, oxygen, or nitrogen, That's a very polar bond. And in all of those cases, the hydrogen end of the bond is very positive. The non-hydrogen end of the bond is significantly negative. So things like water, this hydrogen bonds and dipole-dipole interactions are one of the reasons water has such interesting properties, right? Because it's got very strong hydrogen bond network possibility. Now we move on to both a good and a challenging intermolecular force. London dispersion forces. Now, sometimes these are called London forces. Sometimes these are just called dispersion forces. Sometimes they're called London dispersion forces. I tend to call these induced dipole interactions because that tells you what they actually are. London force doesn't really tell you what it is. Dispersion force doesn't really tell you what it is. Induced dipole interaction tells me what it is. So what is an induced dipole? Last slide we looked at a permanent dipole, something that was always partially positive on one end, partially negative on the other. What if we have something that's not polar? So we can think of this just as simple atoms. So pick your favorite atom here, make it something fairly big. Make it, oh, I don't know, sulfur, selenium, something big. So we've got this simple picture of a couple of atoms. There's a positive nucleus. There's a electron cloud around that nucleus, and we've got two of those. So what happens if this electron cloud, right, electrons are always moving, what happens if at some point this is not a nice circular electron cloud? So if we look at a little different picture of that, sometimes that electron cloud can sort of deform, and instead of having a nice uniform gray, now we've got more electrons over here, so a lot of gray, and not many electrons over here, which makes this side of the molecule look a little negative, and this side of the molecule look a little positive, or atom in this case, not molecule. That is an induced dipole, or that's a temporary dipole. What about its neighbor? Well, its neighbor is sitting here nice and spherical, everything's well behaved, but this neighbor is now all of a sudden seeing a much more negative charge on this other atom. So what happens is once one of these sort of deforms, it can lead to other deformations. So that negative is going to repel some of the electron density, and it's going to push it over in that direction. So now we've got another dipole that has been induced in this atom. So those are induced dipoles. That's the nature of a London dispersion force. Now, these are not permanent dipoles, right? I just arbitrarily sloshed the electrons over in this direction on this one, and that kind of led to a cascade. These can slosh right back in the other direction, and this could be nonpolar or a temporary dipole in the other direction as well. So if we're looking at London dispersion forces, how do we gauge the strength of London dispersion forces? We said dipole-dipole interaction is very strong. What about London dispersion forces? Well, in general, London dispersion forces are pretty weak, but they can be fairly strong if the atom or the element is bigger, because now our electron cloud is bigger and it's more polarizable. It can be deformed more easily. The other way London dispersion forces can become important forces is when we've got a bigger molecule, because now we've got more interactions. And even if each of those interactions is pretty small, if we've got a lot of them, overall it ends up being a big force, right? Think about it, you can lift a car up with sewing thread. You just need a lot of individual strands of sewing thread to lift that car up, right? So that's the same type of thing with London dispersion forces. If you've got many of them, if you've got a big molecule, a long molecule, the total force can be pretty strong. look for different intermolecular forces and intermolecular interactions anytime you're working with any picture of a molecule. Think about how they're going to affect things, how they're going to impact properties, and just try to identify things like ions, things like dipoles, things like uh, large atoms or large molecules that have significant London dispersion forces. See you next time.